Everybody knows that math is super cool, and one of the super cool things about math is divisibility rules. For example, how do we know if a number is divisible by 10? Like 50, is this number divisible by 10? Well, yes, of course it is, because it ends in a 0. That's a simple divisibility rule. We know that a number is divisible by 10 if it ends in 0. In the case of 50, 10 goes into 50 5 times. On the other hand, a number like 27 is not divisible by 10 because its last digit is 7, not 0. Is 27 divisible by, say, 3? Yes, and there's a really nice divisibility rule for that as well. Just add the digits together. 2 plus 7, that's 9. If adding the digits together gives us a multiple of 3, then yes, the number is divisible by 3. Of course, the digits 2 plus 7 add to 9, which is a multiple of 3, and as it turns out, 3 goes into 27 9 times. This is all neat and fairly straightforward, but perhaps we want to answer a more interesting question, like whether or not a number is divisible by 37. One simple trick is to check if the number is 37. For example, this number is 37, and so for sure it's divisible by 37. However, this trick doesn't work for other numbers, so its use is limited. Over 1,000 years ago, were people regularly studying division by 37? Well, not necessarily, but they were adding numbers a lot, and adding numbers is not a trivial task. For example, consider this large addition problem. These days, you might think, well, this is no trouble at all. We'll just reach for a calculator, and this will be a breeze. So let me punch this into the trusty TI-108 and see what we get. Alright, I've typed the problem in, and oh no, we've got an error. These numbers are so big that their sum exceeds 8 digits, and so it can't be done on a calculator. I've heard rumors of other calculators existing besides this one that could potentially do this problem, but I think those are all tall tales. Having no electronics to save us, we may be stuck doing this addition with pencil and paper. Then, proceeding with confidence and perhaps a hint of hubris, we might arrive at this answer. The sum is a bit over 127 million. But when dealing with numbers this large, there's a great risk of making a mistake when calculating manually. Of course, people over 1,000 years ago were aware of this problem, and so they devised a fantastic trick. The trick is called casting out nines, and it can be used to easily check this calculation and gain some confidence in our answer. Beginning with this number on the left, the idea of the trick is to add these digits together, but to ignore or cast out the nines. For example, when I do 5 plus 4, these first two digits, that's 9, so I'm just going to ignore those completely. Then we have 8 plus 2, which is 10, plus 3 plus 3, that's 6, and then this 9 I'm going to ignore, and plus 0 I also don't have to worry about, so we're left with 10 plus 6, which is 16. And then repeat the process with this. 1 plus 6, that gives me 7. I would repeat the process as much as I need to arrive at a single digit. Now I've casted out the nines for this number, and I'm going to do the same thing for the next number in the sum. Adding these first two digits, 7 plus 2, that's 9, so I'm going to ignore that. Then 4 plus 1, that's going to be 6, plus 2, and then plus 0 plus 2, so plus another 2. So that's 6 plus 2, which is equal to 10. Add those digits together, and we get 1. Now the idea is, instead of adding these two huge numbers on the left, if we just cast out nines and add these single digit numbers, 7 plus 1, we should get the same thing as casting out nines from the correct sum. That is to say, since 7 plus 1 is 8, if this answer is correct, when we cast out nines, we should get 8. Let's try it. We see 7 plus 2 here, that's 9, so we can ignore that. 5 plus 4, that's also 9, so we can ignore that. Let's add the rest of these digits together. 1 plus 2 is 3, plus 3 is 6, plus 1, that is 8, and you can see that the equation holds. We casted out 9s on the left, we got 7 and 1, which adds to 8, which is what we get when we cast out 9s from the sum we calculated. While we knew it was possible a mistake was made in adding these huge numbers together, casting out 9s gives us some confidence that our answer is indeed correct. This method of casting out 9s to check arithmetic calculations has been discovered and written about many times throughout history, though the earliest known source of this method comes from the year 950 with the Indian mathematician and astronomer Aryabhata. Historians often give him the 2 in his name to distinguish him from his more prominent predecessor Aryabhata the first, though they are not related. The method of casting out 9s was also described a couple hundred years later by Fibonacci in his text Liber Abaci. This, of course, is the same place where he discussed the problem of counting rabbit pairs, which led to the Fibonacci sequence. So the usefulness of casting out 9s to check calculations has long been well known. But why does it work, and what the heck does it have to do with divisibility by 37? Well, in short, the reason it works is because our number system is base 10. If we have some arbitrary positive integer, I may write it like this: dn, which is the first digit, dn minus 1, which is the second digit, and so on, all the way up through d1, which is the digit in the tens place, and then d0, which is finally the digit in the ones place. And if you recall how our base 10 decimal system works, each one of these digits is representing a number of a certain power of 10. For example, dn is representing dn copies of 10 to the power of n. Similarly, dn minus 1 is representing dn minus 1 copies of 10 to the power of n minus 1. And so on. D1 is representing D1 copies of 10 to the power of 1. That, of course, is the tens place. And then D0 is representing D0 copies of 10 to the 0. 10 to the 0 is 1, so that's actually just D0. Now, when we cast out 9s, we add the digits of the number together and ignore the 9s. This is what the number actually is. What's the difference between the value of the number and the sum of the number's digits? Well, once more, writing out the value of the number, it's 10 to the n times dn plus 10 to the n minus 1 times dn minus 1, and so on, all the way up to 10 to the 1 d1 plus d0. And from this, we want to subtract the sum of the digits. So we want to subtract dn plus dn minus 1, and so on, all the way up to d1 plus d0. The way this subtraction would proceed is pretty simple. We have 10 to the n copies of dn, and we're subtracting 1. So we would end up with 10 to the n minus 1 copies of dn. Similarly, we have 10 to the n minus 1 copies of dn minus 1, and we're subtracting a copy of dn minus 1. So we would end up with 10 to the power of n minus 1 minus 1 copies of dn minus 1. This pattern would, of course, continue until we near the end. We would have 10d1 minus a single d1, which is, of course, 10 minus 1, or just 9 d1. And that would be the end, because d0 minus d0, that would just give us 0. And then we must recognize that this is clearly a multiple of 9. 0 is a multiple of 9, 9d1 is obviously a multiple of 9, and all of these other coefficients are also multiples of 9, because the coefficients are all 1 less than a power of 10. 1 less than a power of 10. So everything here is a multiple of 9. Just to make sure that's clear, 1 power of 10 is 100. If we subtract 1, we get 99, which is of course a multiple of 9. If we take 1 away from the next power of 10, 1000, that's 999, which is of course a multiple of 9. Anytime we subtract 1 from a power of 10, we get a number that's just a bunch of 9s, which is of course a multiple of 9. So all of these numbers in the sum are multiples of 9, and thus the thing itself is a multiple of 9. Thus, when we take a number and subtract its digit sum, the difference is a multiple of 9. Now, of course, adding two numbers together is not the same as adding their digit sums together. However, the difference is only in the 9s. So by casting out the 9s, the difference is gone, and we get a way to check our calculations. For another quick example, of course, 72 plus 41 is not the same as 7 plus 2, which is 9, plus 4 plus 1, which is 5. These things are not the same, but the only difference between them is in the 9s. 72 plus 41, you may know, is 113, and 9 plus 5 is 14. We cast out 9s by adding the digits together. 3 plus 1 is 5, and 4 plus 1 is 5. Note how if we just ignored this 9 to begin with, since it is a 9, we would have ended up with the same thing, just 5. There is some more sophisticated notation and language for this stuff connected to remainders. For example, if we divided 113 by 9, that would be 12 with a remainder of 5. Since 113 has a remainder of 5 when divided by 9, we might write that 113 is congruent to 5 mod 9. If we cast out the 9s from 113, or do what's sometimes called modding out the 9s, we get 5. Similarly, 14 divided by 9, well again, that would be 1 with a remainder of 5. 14 is congruent to 5 mod 9. It is then, of course, also the case that 113 is congruent to 14 mod 9, because they are both congruent to 5. Now, it should be noted, this method of casting out 9s is only a check. It doesn't prove that our answers are correct. It just gives us some evidence to believe we didn't make an error. For example, what's 874 plus 397? If I performed some arithmetic very carelessly, I might say, well, this is 2,180. I'm pretty sure that's correct, but I'm going to cast out 9s just to double check. Again, to cast out 9s, we just add digits while ignoring 9s. 8 plus 7 is 15, plus 4 is 19, so we have 19 there. And then 3 plus 7, I can just ignore that 9. 3 plus 7 is 10, so we have 19 plus 10. 19 plus 10 is 29. I can add those digits together to get 11. I can ignore the 9, and that just leaves me with 2. On the right, again, we add digits together and ignore 9s. 8 plus 1 is 9, so we can ignore that. 0 is just 0, and we're left with 2. So this checks out. By casting out 9s, we gain some additional confidence in our answer. However, this answer is not correct. Indeed, the correct answer is 1,271. If we were to cast out 9s with this, we would get 2 plus 7, which is 9, which could then be ignored, and 1 plus 1, which is 2. So there are infinitely many wrong answers we could get where casting out 9s is not going to help us detect the answer. For example, if we got some of these digits mixed up, that's not going to change what we would get when we cast out 9s, and so casting out 9s would not help us find such an error. This is the correct answer, but what if we got the 2 and 7 mixed up and said that the correct answer is 1,721? Well, casting out 9s here is still just going to give us 2, and so it would not detect the error. But the idea is if you're pretty good at manual calculations, then there's a good chance your answer is correct. And if the casting out 9s works too, that just makes you more confident in your answer. Casting out 9s doesn't just work for addition, but in fact also works for subtraction, multiplication, and even division. I'll show you an example with division because that one's a little bit weirder. Let's say we were tasked with doing 220,811 divided by 346. That wouldn't be super fun, but let's say we do the calculation, we perform long division, and we end up with 638 with a remainder of 63. Now, we think our answer is correct, but we would like to use casting out 9s just to be a little bit extra sure. In order to cast out 9s to check our division, we just cast out 9s for each number and then basically do the opposite of the division. So let's begin by first casting out the 9s, and then I'll elaborate. Adding the digits together, we have 8 plus 1, which can be ignored, and then 2 plus 2, which is 4, plus 1, which is 5. Adding these digits together, we have 3 plus 6, which can be ignored because that's 9, and then we have 4. Going to 638, adding these digits together, 6 plus 3 is 9, so we'll ignore that, and we're just left with 8. And then for the remainder, 6 plus 3 is 9, so I'll just put down a 0. Now, if our division is correct, we should be able to obtain the dividend by taking the divisor, multiplying it by the quotient, and adding the remainder. In other words, take the divisor, which we've casted out 9s to get 4, multiply it by the quotient, we've casted out 9, so that's 8, and add the remainder, we casted out 9, so now that's 0. Now, are these things equal? Well, no, they're not, but we're keeping up with the casting out 9s, which means they don't have to be equal, they just need to be, again, we might say, congruent mod 9. Are they congruent mod 9? Well, yes. On the left, we have 5, and on the right, we have 4 times 8, which is 32. If we add those digits together, we get 5. That doesn't verify, but provides further evidence that indeed our division is correct. So remember, figuring out what a number is mod 9 can be done by simply casting out 9s like we've been doing. And this is the trick that we can use to get a divisibility rule for 37. To get you warmed up for this radical trick, one other thing we can use casting out 9s for is to find the remainder of a number after division by 3. In other words, we can figure out what the number is mod 3. We can use casting out 9s to do this because 3 times 3 is equal to 9. So casting out 9s is kind of like casting out a bunch of copies of 3. A number might be quite large, and thus there might be many 3s to cast out of it, but it can be done efficiently by just casting out 9s. Whatever smaller number we end up with, we can then find what that is mod 3 to quickly find this remainder of the original number after division by 3. In other words, a number n mod 3 is the same as that number n mod 9 and then mod 3. For example, what is 227 mod 3? Again, this is the remainder when 227 is divided by 3. We can find this by first just casting out 9s. 7 plus 2 is 9, so we can ignore that, and that just leaves us with 2. So it's equal to 2 mod 3. Of course, 2 mod 3 is just 2, because 3 goes into 2 0 times with a remainder of 2. We can use a very similar sort of trick with 11, because 11 times 9 is equal to 99. So if we cast out 99s, that's like casting out a bunch of 11s, and thus we can use that as a quicker way to figure out what a number is mod 11. So if we want to find the remainder of a number n after it's divided by 11, again, by definition, that is n mod 11, and the quick way we can figure that out is by first doing n mod 99, which can be calculated by casting out 99s, and then take this mod 11. To cast out 99s, instead of adding single digits like we've been doing, we have to add up pairs of digits. Let's say we wanted to calculate 9,347 mod 11. We could begin by casting out 99s. Thus, we would add up pairs of digits, so 93 plus 47. But since we're casting out 99s, imagine we take 6 from that 7 and put it onto the 93. So in total, that would be 99 plus 41 because we took 6 from the 7. The 99 can be ignored, and we're just left with 41. So then we would have 41 mod 11. 41 is a lot smaller than 9,347, and so 41 mod 11, well, that's pretty easy to calculate. I know that 11 goes into 41 3 times with 8 left over. If you wanted to go through this process of casting out 99s a little bit more slowly, you could have just done the addition, 93 plus 47, which would give you 140, and then continue the process, add up pairs of digits. Because there's an odd number of digits here, you need to imagine that it begins with a 0. So then we could look at it as 1 plus 40, which is 41, and that's how we would get to the same place. Of course, 41 is less than 99, so there are no more 99s to cast out. And those of you who know your prime factorizations of numbers 1 less than powers of 10 know exactly where this is going. Indeed, 37 times 27 happens to equal 999. And so we can find the remainder when a number is divided by 37 by first casting out 999s, which is done by adding up 3 digits at a time. With this technique, we'll be able to find the remainder after a number is divided by 37, and of course, if that remainder is 0, that tells us that a number is indeed divisible by 37. So how will we find a number n mod 37, that remainder after division by 37? First, we're going to cast out 999s, which is going to give us n mod 999. And then this is just taken mod 37. Again, that's because 37 goes into 999. So by casting out 999s, we're just casting out a bunch of 37s at once. And once we've taken out all the 999s that we can, then we're left to take out whatever 37s remain. For an example, consider 249,753. Is this number divisible by 37? Well, to figure that out, I could calculate what it is mod 37. If this number, mod 37, is 0, then indeed it's divisible by 37. To find that remainder, all I have to do is begin by casting out 999s, which means I'm going to add 3 digits at a time. So 249, those first 3 digits, plus 753, the last 3 digits. This is equal to 1002, and again I'm going to add 3 digits at a time. I have 3 digits here, 002, but I'll have to imagine 2 more zeros at the beginning of the number so that I can add 3 digits at a time. So it's 1 plus 2, which of course is 3. This tells me then that 249,753 mod 37 is equal to 3, after casting out all of those 999s, mod 37. There are no 37s left to take out, 3 is quite small, so this is in fact just equal to 3, which tells me there is a remainder of 3 when this number is divided by 37. So no, it's not divisible by 37. But let's try one more example. Consider 180,967. Is this number divisible by 37? Let's calculate what it is mod 37. We can do this by casting out 999s, so add 3 digits at a time. 180 plus 967. That is 1,147, and we can continue again adding up 3 digits at a time. I'll pretend there are 2 zeros there at the beginning so that I can actually add 3 digits at a time, giving us 1 plus 147. That, of course, is 148. This number is less than 999, so we can't cast out any more 999s. So to complete our calculation, we have to do 148 mod 37. The number, of course, is a lot smaller now, so it's pretty easy to figure this out. Indeed, 37 goes into 148 4 times, so after division, there would be no remainder whatsoever. This is equal to 0. Since 0 is our final answer, we know that 180,967 is in fact, yes, divisible by 37. So how can we determine if a number is divisible by 37? All we have to do is cast out 999s, and after doing that, if we end up with a multiple of 37, then the original number was divisible by 37. Note that in casting out 999s, like here, we could have used a trick that I mentioned earlier. We could have taken 32 from 180 and added it to this. Then that would be 99, so we could ignore it. And after taking 32 from 180, well, that would be 148. But again, you don't have to do any clever tricks like that. You can just keep adding 3 digits at a time. If you get 999 at any point, or you see a quick way that you can make it, then that gives you a quick way to simplify things further. But that, my friends, is the 1,000-year-old trick called casting out nines, which can be used to check your arithmetic calculations, and even cooler, can be used to check divisibility by 37. Let me know in the comments if you have any questions, and be sure to subscribe for more of the swankiest math videos on the internet.
I'm unstable, I'm feeling hard to keep the cable cut and unsort the table. If Texas Instruments don't reply, well, I think this time it might be fatal. Wish to sell my own fake, cause I'm jaded.
Hate the odds that I calculated.
Press and pull and pray and push it all the way through the whole blue planet.
Planet faded.
Psych!